Good morning, everyone. I'm Jordan Chivers. I'm one of the Schmidt postdoctoral fellows here. I'm thrilled to introduce our first speaker of the day, Dr. Aishik Ghosh, who is a postdoctoral researcher based in Berkeley and affiliated with Berkeley National Lab and UC Irvine. He develops novel machine learning methods for problems in particle physics and astrophysics with a focus on uncertainty quantification, generative models, and frugal AI. He obtained his PhD from the University of Paris-Saclay for developing simulation-based inference methods and deploying the first deep generative model for fast simulation of the ATLAS detector. In addition to his research pursuits, he also works with the OECD, that is the Organization for Economic Cooperation and Development, on matters of AI and science policy. So please join me in welcoming Dr. Ghosh.
John, for the introduction, and thank you everyone for inviting me to this very interesting school of AI for all of science. I'm sure you're learning a lot from each other's fields. So yeah, I'm going to be talking about AI. I guess the topic I was asked about is AI for fundamental physics. Yeah. Oh, do I need to try that?
Thank you.
All right, perfect. Right, so for those of you who couldn't hear me, you missed nothing. All right, so let's get started. So when no, all right. Okay, so since the topic is fundamental physics, I thought I'll start with this slide. Feel like since as far back as we can remember, we've had some fundamental questions about the way the universe works. What comprises everything? If we zoom in, what are the fundamental elements that describe our universe? And as far back as 5th century BC, there were people hypothesizing that maybe everything is made out of earth, fire, water, air, and so on, right? So this was some kind of a theory. But also, as far back as 6th century BC, there were questions about the theory of errors and uncertainties. So what not just to make a conjecture, but to actually understand the source of maybe your mistakes, which is, I think, equally exciting. I think in today's categorization, we would call these people who make up things theorists or theoretical physicists, and the people who actually test hypotheses and see with how much confidence we can claim certain discoveries, experimentalists. So in fact, that's Peter Higgs, who was one of the people who came up with the Higgs mechanism, and the Higgs boson is named after him. And these are the two people who announced the discovery of the Higgs in 2012. But we still have a lot of questions we still need answered today. One of the main ones is probably the fact that the entire world that you know of and you can think of, light, this stage, the earth, all it constitutes matter. That's the visible part of matter, which is only 15% of all the matter that we observe in the universe. So the rest of it is called dark matter. We understand very little about it, except that it doesn't really interact too much with the rest of visible matter. So we would really like to understand what it is, what's it made up of, what kind of interaction does it have. The other thing is almost all the natural objects that we see are made up of matter. There's very little antimatter that we can find around. And all of our theories are very symmetrical. They predict that there should be an equal number of matter and antimatter particles. So that's also confusing. And we would like to understand why this asymmetry occurs. And there are several other questions that we're curious about, like what is exactly the mass of neutrinos? How do these things work? And another big one is, what about new forces? Are there, besides gravity and electromagnetism, nuclear forces, there's something else? And often, a lot of these theories that try to explain these kind of big questions come up with extra particles. So either for a new force or to explain all of these things, you need to introduce additional terms in your theory, and that often gives rise to new particles, and then we hope that maybe we can discover these new particles to confirm that our theory is correct. So this is the theory, our current best understanding of the the microscale physics in the world. It's called the Standard Model. And we know that it's an incomplete theory, but it explains most of the things we see apart from gravity. So we have these kind of particles, we call them quarks. So for example, your protons and neutrons are going to be made up of the two lightest quarks in different ratios, and then they have their heavier cousins. We also have the electron over here, these are called leptons, and then it has its heavier cousins as well as these neutrinos that it's very hard to see them. And on the other side, we have the force carriers. So these carry things like the electromagnetic force, the nuclear force, and so on. And right in the middle there is possibly one of the most interesting particles of them all, at least the most interesting to me, is the Higgs boson. And this actually gives the other particles their mass. The particles in our theory cannot have mass on their own, so they need to interact with the Higgs field to be able to obtain mass. And that's quite interesting, because it means that if there are if a particle is heavier, it means it just interacts with the Higgs field more than lighter particles. And if there are going to be any new heavier particles that we haven't discovered yet, chances are that they also interact with the Higgs to get their mass. Now, heavier particles are more difficult to create. It requires far more energy. So we need to really pump energy into our system somehow. And we do that by building this massive ring in Geneva and speeding them up and smashing particles with each other. So really what's happening is not that it's not that the particles exist inside and we're just pulling them out. They don't exist until you give them enough energy, and then for a small moment, you can create these new massive particles that quickly decay to something lighter. And the picture we get at the end is this very complicated image of the entire collision. There's a lot of stuff happening. You can see how many particles are shooting out from the collision point, and they hit different parts of a detector. Some of them are calorimeters. They look like you're taking an image. Some of them track the direction of the particle and so on. So different components of our detectors measure different properties. But the point to keep in mind is you don't actually get a picture of what happened at the collision. You only get a picture of the daughter particles that whatever you produce decays into. So we have to really guess what might have happened in the middle. And right. So this is how we build the detector. So you can see the size of, for example, the detector I work with, the Atlas detector. This is the human. So it's kind of big. And each of us specialize, we focus often on one small part of the detector. That's your contribution during a PhD. I contributed to the calorimeter. And all of us come together to build this. And the point is, we know it's an incomplete theory. So we want to break our own model. It's like we want to find a bug in it, right? But unfortunately, no matter how hard we try, we haven't really been able to find ways for our own theory to crash. So, which is a shame, because the easiest way to find new physics is to find where our current understanding stops working. But since the discovery of the Higgs, we haven't really found a lot of new things that are not explained by our standard model. So what that means is there are no easy breakthroughs. So we really have to push the frontiers in terms of making very precise measurements, going the highest energies we can possibly access, and also just studying places in the parameter space that we didn't dare to study before, because maybe it was just too complicated, too much noise, too much background. So yeah, and all of this that I'm saying is just about the LHC, and of course fundamental physics is much, much wider than LHC physics. This is my experiment over here, and the Large Hadron Collider has 3 more experiments. But besides that, there are gravitational wave observatories. You've been listening to discoveries that LIGO were made recently. There are neutrino observatories that try to find neutrino particles coming in from the sky, and there are also neutrino experiments where we generate our own neutrinos and we study them. And of course, we are all studying and trying to find new physics in different ways. I will not be able to cover all of them, so I'm going to give LHC as an example of the kind of different questions we can ask and how AI can help solve very different kinds of problems that come together to try to make us understand the core of how things work. Right. So the first thing to recognize is, so if you think about pattern recognition, what are the questions we actually are asking in fundamental physics? This is the one kind of a question: is this a Yeti? If you ever actually take a picture of a Yeti, you can answer that question definitely and say, yep, that's a picture of a Yeti, and so that's a discovery of a Yeti. So one picture gives you a definitive answer of whether something is the new object you were searching for or not. This is not something you can do with our kind of data. You can't look at one collision event and then say, ask the question, is this a Higgs boson event? So was there a Higgs boson in the middle? It's not possible to give you an answer because the final measurement we make could have come from many different processes. One of them is the Higgs boson process, but there are many other processes that can give rise to exactly the same final measurements. So we can only make statistical questions. And besides this problem, the other issue is quantum interference. So in quantum mechanics, we know that if you have the same initial state, so let's say two quarks, right, and the same final states, again, two quarks and four fermions here, the same for the other diagrams. You can see that the intermediate states are different, but if you have the same initial and final states, then all the ways you can go from the initial state to the final state, all of them, if they can occur, they will occur simultaneously. And in fact, they might even interfere with one another. It's kind of like thinking if you were to go from point A to point B, and that's the only thing you know, that you've gone from A to B, then all the paths you could have taken from A to B, you will actually take all of them simultaneously, and you might even collide with your other version of yourself. So that's roughly the weird way quantum interference works. And so then if you ask, is this event coming from a Higgs? Well, it's possible that the fact that this event happened has a contribution that comes from a Higgs process, but also a contribution that comes from a non-Higgs process, and they both have quantumly interfered. So the answer to the question is even ill-posed. So really what you can ask is the data compatible with my hypothesis that the Higgs field exists and it couples in this way with the other fields and so on. So that's really the only question you can ask. And so the questions we ask are usually statistical in nature. And since we like to ask these kind of questions of probability, we like to also try to get probability densities. So theorists will calculate probability densities of different kinds of things happening. Like if you're going to see the mass of two photons, it's much more likely that you see that with lower masses than with higher masses. And similarly, when we get data, we bin it into histograms. These histograms are a very nice and convenient way to try to look at densities. And so what we do often is that we will do a background simulation in blue here, which is to say if there was no new physics and things are only explained by what we currently understand, then they will look like this. And then let's say we're searching for a signal, which 15 years ago was the Higgs boson, then you would say, okay, if this signal exists, then it should enhance this distribution at the tail over here. And then you look at data. Of course, with data, you can't separate signal and background in a definitive way. You just get this full thing, but you can compare this to your simulations and say that, well, this data looks quite compatible with this particular combination of signal and background. So maybe this is very compatible with the data. And in fact, that is how the Higgs was discovered in 2012. So here, the blue line you can see is the background only simulations, and the black dots are the data we're starting to collect. Each day we collect more, so the whole histogram goes up. And at some point, we start to see a little bump emerging over here near 125 GeV, which can't be explained by the blue line anymore. But as soon as we superimpose this red signal plus background, it perfectly explains this little bump. And that's how we claim the Higgs discovery. All right. So I hope I've convinced you that in LHC physics at least, and in many other kinds of similar experiments, simulation is very important to analyze our data. So we usually have three important components. One is the simulation, which involves calculating what's happening at the collision point, but then also subsequently what happens to those particles, which is called these things, spiral showering, harmonization, and then how that interacts with the detector. And these are actually a software that's written by different parts of the community. These are usually done by theorists and this one by experimentalists. And then from the data, the actual collision data, of course, you have the collisions, but then we do not collect all the data. We in fact do a very strong filtering using trigger algorithms. And we select something like we throw away 99.998% of all the data because we are we're generating way too much, and we need to be smart about keeping only the interesting samples. So of course, the way you do the filtering affects all your subsequent studies. So you better make sure that the quality of the data you're collecting is good. And finally, or you take your data analysis algorithm, then you often fine-tune them on your simulations and then apply them on data. And this involves clustering, classification, regression, and then statistical inference itself. So my question to you is, which of these boxes that I've shown do you think machine learning comes in?
All three.
All three. Okay, absolutely. Okay, you've got the answer on the first try. That's true. So here it's obvious: clustering, classification, bread and butter machine learning. I will show you examples from each of these: simulation, filtering, as well as statistical inference, where we actually use machine learning, and it's really revolutionized the way we do things. Excellent. So the even bigger picture is, I'm not going to go through every point here, but this is roughly the kind of stuff theorists do. They will generate promising hypotheses that the experimentalists can then go on and test. But they also have to figure out which hypotheses are actually testable, because there are lots of great theories that have absolutely no way of being confirmed or ruled out with the experiments we have now. And also, once the experimentalists put out some results, the theorists will combine results from different experiments, observatories, try to get a consistent latest map of what theories have been ruled out and what hasn't. And they also maintain these the first half of the simulation packages. Experimentalists test hypotheses, they communicate the results back to the theorists, and for their work, they often need to maintain fast simulation algorithms, intelligent data acquisition, experiment monitoring, and even in the beginning stage of an experiment, they have to design the detector itself. And everything I said here is starting to use machine learning in one way or the other. I'm going to start by giving an example of fast simulation. So as I said, there are two parts of simulation. There's the collision part, and then there's the detector interactions part. This is usually done by this package called Giant, which is, it's a really useful package, not just used in high energy physics, but also used in medicine and so on to simulate how particles interact with different material. But it's very accurate, but very computationally intensive. We do have the CERN worldwide computing grid, which consists of computing farms from all over the world that come together and try to help us do our analysis. But nonetheless, we don't have enough resources to keep going with the algorithms we have now. So this is a plot from the Alice experiment of the projected computing resources they're going to have over the coming years. And then the blue dots is the expected amount of resources they would need given the current algorithm. Then you can see that there's a huge gap in the upcoming years, which means we just need to come up with faster, more efficient algorithms. Otherwise, we won't be able to make the most of the data we're about to collect. And if you look at this chart, the simulation is the largest consumer of all the CPU resources we have. And in fact, 75% of that comes from calorimeter simulation alone, which is a particular part of the detector that's which is really slow to simulate, because what happens is when a photon comes in and interacts with the calorimeter, it starts to shower, which is it converts into two electrons, and the electrons will give off another photon, and so on. So it starts to make a shower in the detector. And yeah, as it goes through, it gets quite complicated. And in the end, what we record is not this full time evolution of how things split, but the final three-dimensional images, right? So the question is, if we only record the final images, then why do we need to track the whole time evolution? Maybe we can make a shortcut directly from the properties of the particle to the image. This is not something you can do with just the simulation software, but maybe you can do this kind of things with generative models. You've seen nowadays that generative models can create these amazing looking pictures, right? So this is not only amazing, but it's hiding a little message behind, the same message here and the same message here. So it's very cool that things like Stable Diffusion can make images like this. So the question is, if they can do all of this, why can't we use them to try to do our simulation of 3D images? And so this is something we've been studying for a while. So before diffusion models became all the rage. So the first generation of generative models included the variational autoencoder. Here, the big picture is that if you can train a neural network, it's a combination of two networks. One is the encoder and the decoder. And the idea is that you take your training images and the encoder learns to compress them. And then the decoder learns to decompress them and to try to get the reconstruction to match the target. And there's a little trick in the middle where you try to enforce the latent space to be Gaussian and be able to generate new images as well. So the idea would be, in the end, once the thing is trained, you drop the encoder and you can just plug in random numbers into the decoder, and it generates for you new images that come from the same underlying distribution. Yeah. The other one was generative adversarial networks, where also you have two networks. You have the generator and the discriminator. The job of the discriminator is to separate the images coming from your training data set versus the fake ones generated by the generator. And then the job of the generator is to fool the discriminator. So the only way it can do that is to generate more and more realistic looking images. So hopefully by the end of the training, the fake images look so realistic that you might as well just use them for your simulation. And so the first paper that started it all was this one, Tallow-GAN from 2018, where the GAN was trained to reproduce the Geant distribution. And it was done on a proof of concept toy calorimeter, a small one, not as big as the actual one we have, but it's still reasonably complex. And the authors managed to show that, so here the filled in histograms are the true distribution, and then the ones that are bordered are generated by the GAN. And it does reasonably well at reproducing these kind of distributions, not perfect everywhere, but it's a great proof of concept. And in fact, the interesting thing is this data set for quite some while then became a benchmark for fundamental GAN research. So whenever the latest version of a GAN used to come out, which was quite common back in 2018, they were tested on a few standard data sets like MNIST and celebrity faces, and also sometimes on the scalarimeter image to show that, look, my version of a GAN can reproduce these distributions slightly better than before. So that was cool to see that we were being represented also in the machine learning community. And a year down the line, the Atlas experiment put out some first results of actually training such a model for the actual detector, although from a very small part of it, and integrating it into the full C++ simulation pipeline, which means that you can, for the first time, really compare the speed, memory consumption, and so on, and see if this idea of using generative models would actually be viable. And so so GANs and VAEs were both trained on cropped 3D images in the central part of the detector. And the validation used, so it was trained on the raw images, and the validation was done on much higher level features that were calculated based on the images. And there was also an interpolation test. So the training data set was only available at 9 log space energies, but you can see, for example, the GAN was trained on 16 GeV and 32 GeV, but also reproduces the 25 GeV distribution without ever having been trained on it. So We were also testing the interpolation capabilities, which are important when you only have a finite number of points in your space that you're training on. In terms of speed, it was seen that the model was just, even after integrating it into the pipeline, using CPU only, no GPUs, and also no batching, single image simulation at a time, it was still just orders of magnitude faster than Giant. So to the point where you didn't even need to speed it up anymore. There were other parts of the chain that were slower. And in terms of memory also, it was orders of magnitude smaller, the footprint compared to baseline fast simulation methods. But that was not the end of the story, because these models had one particular challenge, which was that they could not handle the different geometries of the detector. So already for the results I just showed, they were trying to handle 8 different configurations. So think of this is a 3D image. So you have different layers of the calorimeter that are one on top of the other, which have been shown here as side by side. So if this is the middle layer, then the alignment of the layer in front of it, there are 4 different possibilities. Either this layer covers mostly the top 2 cells and not the last one, or in the other extreme case, it can cover mostly the bottom 2 cells and not at all the top one. And depending on the alignment, the image, even though the fundamental image is the same, the image recorded can look very different. And this was a challenge which was solved by conditioning the GAN as if these are 8 completely different sets of data, and you just learn to generate each of them separately. But this would not scale, because when you try to do the full detector, this 8 quickly becomes hundreds. Right. The other challenge was things like this, where the cell sizes change. You never see this in typical natural image data sets, because the pixels can be considered tiny. But here, each cell, the size can change, and if the size changes, these are all basically the same underlying image that have been shown in different representations. So you see how different they can look depending on the properties of the cell. This is also something that was very tricky to handle in this case. And so what can you do? One thing is, a naive idea would be to train hundreds of generative models, and that's definitely something that was done. And then which is interesting. But the challenge is, of course, that the challenge is that validating one generative model is hard enough. Validating hundreds of generative models is next to impossible unless you can find some optimized way of doing it. So you really have to look at all of these plots for one model and then do it 100 times. So we were thinking, isn't there a smarter way to handle this kind of a geometry problem? Fundamentally, the images are the same. If we could just tell our generative model the concept of cell size and cell position, maybe we would learn to interpolate, and we would realize that the difference between this cell and this cell is just that this is bigger, so I need to deposit more energy in this cell. And then if 2 cells are close by, then they're probably going to be correlated in terms of energy. So to do that, we explored autoregressive models, which generate cells one at a time. And so it always has information about the history of the simulation. So if it's simulating this cell, it already knows what's happened in the cell before. And it's conditioned on the properties of the cell, so it can adjust the energy deposition based on cell properties. So this is the idea. You take a image, you flatten it out using some ordering, and then you can use these kind of autoregressive models that not only are trained on the images, but also have a given properties of the cells, like the width in the one direction, width in the other direction, and so on. And with that, we see that not only do these models work, but they also generalize to completely new geometry that have been never seen in training. These are 2 examples of geometries the model has never seen. This has 24 by 24 cells. This has 24 by 12 cells. And we can see that nonetheless, the model is able to reproduce the average looking images for both of these geometries. So that's quite exciting. It means that it will not only be able to generate cells that are in the training data set, but also anything in between and interpolate. The other exciting thing was that this, for the first time, was able to handle boundary regions. So if you look carefully, the cell sizes on the left are a lot smaller than this abrupt change to in the middle, and then the cell size on the right become bigger. And this is not something that was ever tackled before with generative models because it's very challenging to do this. The model has to know that, well, here 2 cells here is equal to 1 cell there. And with these autoregressive models, you can see, so this is the true geometric form, and then this is the autoregressive model, which almost perfectly reproduces this. And this is a baseline model, which is not conditioned on cell properties. And you can see that it doesn't do a very good job. It can't even get the energy right in the middle. All right. The other angle, which by which you could try to solve these problems, is to forget about cell sizes and say, I'm going to simulate everything at the maximum precision. So I'm going to go to point clouds, generate point cloud energies, and then you can just cast them into cells as you like with post-processing. And this has recently been compared. It's between, and turns out this is actually a much more challenging problem because you're really simulating at the maximum precision. And even if you then do the comparisons at the cell level, a model trained on the cells outperforms a model trained on the point clouds, but it's something that's still quite interesting to us. So we are continuing to explore this. And in this comparison also uses the latest generative model. So it's all diffusion for cells, diffusion for point clouds, and so on. So yeah, it's not the generative model that's causing the lack of performance. Yeah, so it's interesting to see the two opposite ways of trying to solve this problem of cell properties, and it will also be interesting to see how things evolve in the future. The other exciting thing is that I talked to you about the Atlas experiment trying to simulate this kind of a calorimeter, but similarly, our rivals in CMS have been trying to simulate this kind of a calorimeter with generative models, and there are several other experiments that are trying to build their own generative models for their own detector properties. And often the neural network architecture you use is very different. This one uses simple dense networks. This one uses convolutions. This one is very, very different. And then you can ask yourself, if now our model can handle different cell sizes and so on, then we can have a more common architecture, kind of like in natural images where you had the DC GAN that came out and it could solve images of people, but also images of rooms and so on. So maybe we can have a more common architecture that can solve these different kinds of detector properties. And there we would be moving towards something similar to what's quite fashionable now, which is foundation models. You could train these models on a variety of detectors, always conditioning on the properties of the detector, and then release that as a pre-trained model, which can be quickly fine-tuned for your particular detector in your experiment. And that would save many years for each of these experiments who are trying to design their own generative model. And of course, another benefit is if you're trying to design a new detector, you can quickly fine-tune this on your new detector without having to first upfront simulate hundreds of thousands of samples with the slower simulation and then fine-tune your simulator. All right, so I think I've talked quite a lot, and I'm going to take a little pause to see if anybody has questions. Excellent.
Thank you. That's so fascinating. I'm curious, what do the errors in the different GAN approaches, so the cell geometries and the point clouds, what do the errors that you have there tell you about what the model is specifically using in order to be accurate? Like, what is the model paying attention to? Is it like local correlations between the geometries, like that's why the point cloud is less accurate? Or have you looked at that? Like,
yeah, that's a very interesting question. So what are the models paying attention to, because of which some of the models do better than the others? This comparison is not it's not my paper. It's from some colleagues. So I wouldn't be able to tell you about this one. These ones are stuff I know very closely. So yeah, there are. So when you work with point clouds, you're always using some trick, because it's really hard So the best point cloud models that are out there are either, so some of them on the market assume that all the points are uncorrelated. And so it's good to like generate point cloud images of aeroplanes and so on, but where the total number of points gives you some physical meaning, like the more points you have, the more energy you have. These kind of things, these models are not very good at modeling. So we instead use things like transformers and graph neural networks, which can handle this kind of information. And there too, you need to come up, it's just the number of points is so much more than what is common. We go to something like, we can go up to hundreds of thousands of points per image. And I think we've successfully been able to go up to hundreds of points where like you can, the model learns all the correlations between all the points. So if you go any further, then you need to make some kind of assumption of like independence of the points or being able to use the same network for different parts and so on. So yeah, so if we could just scale very naively to hundreds of thousands of points, I think it would do a lot better, but the models will get just ridiculously big. Yeah.
And just one more question for the Paganini et al. 2018
Yeah.
slide. So there were two predicted distributions, I think, from the GANs. It's the one after this one.
Yeah.
So what is the difference between the pink and the blue?
Yeah, okay, that's a good question. Yeah, I definitely skipped over this. So we have different kinds of particles that we want to simulate in the calorimeter. So the top, the blue is they're positrons, which are like electrons but with positive charge. The pink one is a photon, and then the yellow one is a pion. So the first two are relatively easy compared to the pion. This one only interacts with electromagnetically. So yeah, so and this calorimeter is an electromagnetic calorimeter, so it's meant to measure these two particles. It only measures some energy of this last particle, so it's definitely more challenging to model this because there's incomplete information.
And is there, again, similar to the first question, is there a reason why the errors are still occurring for the blue?
Yeah,
the
yeah. I
particles
mean,
corresponding to the blue?
it's a challenging problem. That's the main reason. And GANs are very difficult to train. You need to use all kinds of tricks to get them to even like avoid mode collapse and so on. So this paper, I believe, was using things like label smoothing and so on. So whenever you put different regularizer, it pushes the solution towards some direction. Yeah, I think subsequent papers have done much better. For example, there are a couple of papers using normalizing flows for exactly the same data set where they pretty much get this bang on. They're able to reproduce this really well for this geometry, but then turns out that if you go much higher granularity, then those models don't scale. But then there's some other tricks you can use.
Thank you. This looks like a really useful approach.
Hi, I just wanted to follow up on, I guess what you'd said where you were saying that like think cloud-based models that make independence assumptions don't work. And I guess so and you were saying just because there's sort of like these global, I guess, properties. But can you explain that more? Because it seems to me like if we have like in I guess the actual distribution in the real world, it could be represented by a probability distribution. And so if we had the right one, it seems like we should be able to use an independence assumption, and that would be fine.
Yeah, I guess there are different ways of doing it. And for some of them, in principle, it would work, but there's also a question of like what is in principle good and what is in practice good. But for some of the models, it's something we've been trying for a while. So maybe the models we started studying were pretty old, but there you didn't even the model wouldn't tell you how many points to sample. You had to just choose. Whereas so you could have a first generative model that chooses the number of points, and then the second model that samples that many points. Yeah, so you could probably do something like that. But yeah, I guess point cloud based methods are still evolving compared to image based methods that have been around for a long time.
Okay, but I guess in theory, if we, for example, did have a point cloud based method and we can sample from it like a million times and then create like a very fine grained histogram
Right.
essentially.
So the problem there is each point is associated with an energy. And one of the distributions we have to get right is the total energy in the image. So if you have like on average each point has, I don't know, 1 GeV, or it's going to be less, but then you really need to make sure that the total sum of the energy is correct. So if you sample 10 times more than you were supposed to, you're going to get 10 times more of the energy.
And there's no way to just normalize by the number of points.
Yeah, you could. Right, okay, so then the points would be, the energy of the points would look different in your generations versus your true, but you can probably, yeah, you can probably not care about that. Something you could try.
Yeah, thank you.
Hello, I'm just asking what the model gives. Does the model predict energy spectrum or 3D image of cell?
Yeah.
What is a cell? I also don't know.
What is what? Sorry.
A cell. You
A
mentioned
cell, oh, of course, yeah, I'm sorry about that. Okay, so think of this is a nice representation of what a calorimeter would look like. So what you can see is like in an image, if you think of a pixel, you can map that to the concept of a cell in a calorimeter. So this block, you see one there, this is made out of many small blocks. I hope you can see it from there. So it records energy, and we have no information that's finer than one cell. So if multiple particles deposit energy in the same block, we will just measure the total. So that's the smallest amount we can measure. So we call, yeah, so that's the cell. And the way when we apply image based generative models to calorimeters, we treat each of them as a pixel. But the difference is in image models, the intensity is it doesn't have any very fundamental meaning, right? The total amount over here is between 0 and 255 usually. Whereas for us, the total energy is a property on its own that needs to be modeled well. So the sum of all the energy recorded in each of these cells needs to also represent the truth. Does that answer your question?
so how can you make a cell like some cells are big, some cells are small?
Yeah.
What does it mean?
That yeah, so you can see here these cells are pretty big. You can see each of them pretty clearly. Here you can see that they're big in this in the vertical direction, and in the horizontal direction they're so fine that you can barely notice the division between cells, right? So it's as if your pixels would be massive over here, and then the pixels are very fine in the horizontal direction and very long in the vertical direction. Thanks. All right, awesome. So where were we? Right. So another question that might come to your mind is why don't you just surely training a generative model on training data is like a very convoluted way. Why don't you just reuse the training data itself to get your images? And there are a few reasons why you wouldn't want to do that. The first is it's not as memory efficient. You know that now, like these large language models and diffusion models, they can almost compress all the information on the internet into just a few gigabytes. So similarly here, we see that the neural network sometimes is a few megabytes, while the training data itself might be in gigabytes. So it's just memory efficient. It also interpolates, as we saw, between different points in the training data set. So it can effectively generate much more data than the training data set. And also the other interesting point is that these neural networks are self-regularized, and then you can add regularization. And so it often smooths over statistical fluctuations in the training data set. So it can sometimes give you more information than the training data set itself. And let's see an example of that. So here, this is a study specifically done to study this property of GANs being able to produce more data than the training data itself. And the first study is done on a simple Camelback function. So it's like two Gaussians, all right? So here, the black line represents the true probability density, and then you sample 100 points from it, and you call that your training data set. So that's the blue distribution. You can see that there are some fluctuations where it goes over, under, and then you train a GAN, and you sample from it, And you see that the GAN produces this orange image, and you can already see that some places where you have fluctuations in your blue distribution, the GAN kind of smooths over them. So you can hope that maybe the GAN does better. And so that's what they measured in this plot here, where the y-axis is the error of the distribution that's estimated. And so this is the error for just from the training data set itself, the sample, and the error bar tells you, like, if you choose a different 100 samples, then you basically get this uncertainty. And on the other hand, with the GAN, you can generate up to 100 points and you'll be here, but actually you can go ahead and generate more points, and about 3, 4, 5. And you can see that the error continues to reduce, which means it's still producing useful information. And at this point, it saturates, which means that this is really the limit of how much information it has. And so the error is equivalent to if you had taken samples, not only 100 of them, but in fact, a bit more than 500 samples. So this is what they call gamplification. You get more data than you train on. And of course, just to make sure everything still makes sense, you can fit an actual, so if you knew that the true function was a camelback, you can fit the mean and standard deviations, and then that will give you the best possible result, because yeah, your GAN shouldn't be able to do better than a model that has all the inductive bias in it already. But an open question is, okay, we can do the study on a very simple toy problem, or in any problem where you can really generate 10 times more samples to confirm that the GAN is able to do similarly. But what do you do in a realistic setting when the training data set is all you have? How can you tell if the GAN can go up to 2x, 3x, 4x, or 5x? And as far as we know, we haven't figured this out yet. If some of you have ideas, then maybe you can come up with a way. That would be very useful. The other thing I want to talk about is evaluation of generative models. So as I said, there are lots of plots we look at for even just one generative model. And then somebody asks you, oh, but you are looking only at one-dimensional marginals, why not look at two-dimensional plots? You look at them, and someone asks you to look at something else, and something else, and something else, and something else. Very quickly, you realize that maybe I'm just doing a PhD in plot evaluation. Or at least that's how I felt during my PhD, and I was training GANs. And it kind of reminds me nowadays when these kind of articles come up that say, ChatGPT is, they're like taking hundreds of people in Kenya and paying them very little to like manually evaluate ChatGPT and make sure it's not saying stupid things. So surely there's a better way than making humans now evaluate generative models. And so in the old days, it would take us a while to come up with an algorithm that does your simulation. And then the fraction of time you spend on evaluating it was significant, but not this crazy. Right now, the model learns a simulation function on its own, and every 5 days you have a new generative model, and then evaluating it can take a lot of time. So there's been some interest in how we can automatically evaluate generative models, and it's a deep question in all three fields. There are some typical ideas like versus time distance. This is essentially if you take one distribution and compare to the other, this measures what is the minimum you have to move each piece of like a smallest block you can think of to make this distribution look like this distribution. And there are other such distances that have slightly different definitions, Fischler distance, likelihood ratios. And I'm not going to go into the details, but I'm going to just tell you where the research is at the moment. And there's this very nice paper by Raghav Kansal and all, who have tested a whole bunch of these metrics on well-controlled problems. So first, a Gaussian problem. So if that's the truth, that's some Gaussian with like there's some correlation between the axes, then you can shift the Gaussian or change the width or add two Gaussians and so on, and see which of the metrics will pick up all of these different kinds of distances. And then they tested also on a physics sample of jets, and then they so the true distribution is in blue, and they do different kinds of modifications like smearing it a little bit, shifting it, or discarding off the tail. Because the tails are often something that in physics we care a lot about, but generative models don't. model very well. And then the crux of the result is that they tested all kinds of different metrics, and they found the three that were unbiased were the Wasserstein distance, Frischle-Gaussian distance, which involves and the MMD, both of them involve fitting a function to your observables and then calculating distances. And the FGD was the most promising in terms of always catching the different differences. But this is just the first study, it's a great first step towards this, but we still need to study it on different kinds of data sets, but also these metrics are good to they give you a number. They say this is better than that. But in the end, what we want is something more interpretable. I want to know, I would ideally like these metrics to tell me a few different things. Should tell me that, your model is great in the bulk of the distribution, but fails in the tails. Or it gets the higher moments right, but not the lower moments, or the other way around. Or that it's good at everything else, but doesn't interpret it. Or it could be more physics based, like it models the energies right, but not so much the smoothness and things like that. And once we get these things, the nice thing is stuff that we develop for generative models or machine learning methods in general, often you can backport them to your traditional algorithms. And so that would definitely be something we can do. Because in experimental physics, we love uncertainties, but we don't usually put uncertainties on our detector simulations because we just don't know how to quantify them. So anything we pick up from these might also be useful for our simulators. Right, so again, this is a topic of active research and lots of room for new ideas to come up. So I talked to you about simulation. Now I want to give you an example of how machine learning can be useful in curating the data itself. I guess I'm close to the end, right, of the first part?
Like 5 minutes.
Yeah, okay. So I'm going to go quickly through this, but yeah, I have definitely more content than time, but that's fine. We can just, I can give you a taste of the different things that we do. So triggering, as I said, we get about 40 million collisions per second. If you think roughly, if you're storing things efficiently, you have 1 megabyte per collision, so that's 40 terabytes per second. It's not something we can write to disk. So we throw away most of our data, and in the future, it's even going to go up to 100 terabytes per second. So we need to come up with a fast way to analyze all of this data, not completely, but just the first pass to reject all the completely boring events. And even neural networks on GPUs are too slow. So you need to come up with a better way. We call these algorithms trigger algorithms, and they're very simple. Most of the time, the decision functions are very simple, so you can apply them quickly. Things like just take the moment of an electron and say, if an event has more than this much momentum for the electron, then you just select it for the next round of analysis. Or 2 jets. The most complicated thing is sometimes a few different jets and their properties. But in our offline analysis, where we have all the time in the world, we do far more complicated algorithms. We want to fit all kinds of different functions, try to resolve these traps and so on. So the question is, can we not do more complex pattern recognition at the trigger? And the answer is that there's actually now been a lot of work on these hardware called field programmable gate arrays, which look something like this, where you can deploy your machine learning models onto these, and then they can do inference. So you train them on your cluster, and then you deploy them here, and then they can do inference at the speed that you need. But there's a lot of limitations. So you can't just like put a massive transformer model, you can't put ChatGPT on that. There's you need to be smart about the bit precision because the memory is important, and also the number of operations you do. So sometimes one activation function uses more operations than another one. So you need to be smart about all of this. And so you need to co-design your machine learning model with the hardware requirements. And luckily, our colleagues in the rival experiment that I talked about, CMS, they have come up with this package that helps you do a lot of this co-design. So one of the things they would do is pruning. So you get rid of the connection that you don't need. You train your model with a L1 regularizer that forces unnecessary weights to go to 0. And in fact, you do it over multiple iterations. You train the model once, then you train it again with this L1, drop the lowest weights, you do it a few times. And then you can get, they showed in this one study that you can get 70% reduction just by doing that. You also want to be smart about how you're representing the weights of your network. You don't often need the full precision. And here they did some studies and showed that the integer part of your representation, they can bring it down to 6 bits and still get roughly the same performance, and the fractional part to 8 bits. That's interesting stuff that they've been working on. And of course, the model architecture itself also matters. So here they showed how to find hyperparameters of a convolutional network that is both accurate and small in terms of total bits used. So you would like try different models and find the one that's to the top left corner. So the x-axis here is the amount of bits used, and then the y-axis is the accuracy of the model. So top left is the best. Okay. Some questions here, but okay, I'm just going to go ahead because we have a couple of minutes, unless you want to ask a question about this. Yes.
For the filtering, I wonder if you've considered restricted Boltzmann machines for detecting anomalies, like maybe if you could detect how it's different from the system, right?
Yeah, okay, that is very interesting. So this is definitely, I am very interested in trigger, and I've been working on it in different ways, but this is not my work, so that's the first thing. They have been studying a few like anomaly detection is a major thing as a trigger, so they've been doing that with simple things like autoencoders and stuff. Also with kernel machines, don't know much about that. I saw something about Boltzmann machines. I don't know much about the details, so you'd have to Google to find out exactly what they've done.
I was just curious if they tried it, but
Okay.
it
We
sounds
can
like
chat
they
about
did.
it afterwards if you think that's a good application. It's possible that nobody is just not occurred to someone, and it's a good idea.
Okay, thank you.
All right. The last, okay, I'm gonna skip.
I just have a quick question.
Yeah.
What does it mean to have an anomaly in this field? Because I mean, I just feel that you might be filtering information that's actually useful to you, but I just wanted to understand what you mean with anomaly.
Yeah, that's it. Okay. Yeah, so that's an important point. How do we choose the events that we're storing? We have some first principle reasoning behind what we think might be interesting. There are particular physics processes that we want to study, and we know that these kind of particles will most likely decay to high momentum electrons or something. So if there are 4 electrons, we are very confident that this is going to be an interesting event and so on. So we have some first principle knowledge, but absolutely we might very well be missing something if we're not very smart. And so there are this idea that I was about to skip tells you how to overcome that. So the idea here is to train a generative model online on the trigger, because you can't store all of the data, but you could. The idea suggests that you could try to train a generative model on the fly, try to memorize some of that data, so that afterwards you can just like generate synthetic events from your generator and try to understand if there's really something in the data that you've been missing. Right. Okay, the last thing I want to say before we take a break is communication of results. So this is very different from what I've been talking about before. In fact, in our community, communicating results is not just writing a paper about it, but we actually have to give more useful information to our colleagues who are theorists. So our theorists only care about the fundamental interaction that are going on, like this. But in fact, these are not things that are measured. They have to interact with the detector and so on. So we need to do a process called unfolding, which is to remove the effects that have come from the detector, so that the theorists can work with this cleaner data. And this is kind of like maybe removing distortions that come from your camera or something. So it's often also called a deconvolution. And there are generative models that do super resolution, right? So you could think of applying them, but as you might know, there's this famous problem. You take this low resolution image of Obama and you apply these generative models, and suddenly, right? So this comes from the bias of your training data set. So the training data set you use biases the results you get, and we don't want biases in our physics applications. We actually don't even want biases in our human applications, but that's not my work. So we have to, on the other hand, if you use classical methods, then you can't do unfolding in high dimensions. we have to find other ML methods, and these ideas have been around. So there's a couple of ways. One is a very clever trick which just trains two classifiers iteratively to get you the correct distribution. So here we have four categories, all right? So this is the data you actually recorded in your detector from the collisions. So this is the real data. What you want is the data without detector effects, the truth. This is something we don't have access to. We instead have access to simulations at the detector level, but also simulations before the detector level. So we know the mapping from simulation to generation. It's called generation, this part, in simulations. So in principle, we could try to learn this mapping and then apply it here. But of course, like we saw with the Obama example, if there are biases here, it'll get transferred to there. So when you first do it in the first round, you get exactly that. The prior here is the bias essentially, and your prediction in blue matches the bias in the simulations. But if you train them, you do it in an iterative procedure, you can show that slowly over multiple steps, you can leak information from the data to the generation. So until your final results start to represent the truth. And this is done by reweighting the simulation to the data in the first step, and then pulling back these weights. So now your samples have weights, and then you reweight the data set here, you push them forward, and you do the whole thing a few times, and then you can get this kind of result. And the weights come from the classifier. I'm going to skip this. And then you can see from an example here. So the data is in black. Usually you don't have access to the truth, but for this study, the truth is in green. And then you can see that this iterative procedure in red manages to capture the actual green distribution without ever actually having access to it, even during training. All right. Oh, okay. I wanted to say that recently we've been able to use diffusion models to also do this and achieve the kind of accuracy that you couldn't do before with generative models, mainly because they didn't have the kind of power we have now. So state of the art before used normalizing flows, and the kind of performance is much better now with our diffusion models. So hopefully we will have more than one way of doing this kind of unfolding in the future. And a quick example of why we want to do unfolding in high dimensions. So this is an example of data from like decades ago that was unfolded by the experimentalists back then, but they did it in linear space. And our theorists later realized that, wait a minute, we don't want this in linear space, it's much more interesting in log space. But when they converted to log space, this one bin in linear space becomes this massive bin in log space. And so they miss all the information that's hidden in here. And look, the reality, like there's a lot of interesting structure here. So instead, if you do it in red with this machine learning method, then you don't need to bin your data into histograms anymore. So you can get, even if like 10 years, 20 years down the line, you want to change the binning or get rid of the binning or turn from log space to linear space and so on, or even compute completely new observables that are some combination of the ones you've unfolded. Since the whole thing is high dimensional and unbinned, you can do all of that with these modern ways of doing unfolding. Right, okay, so the conclusion is, for the first part, that hopefully I've shown you a few examples of how AI is used in simulation, data acquisition, and even a smaller glimpse of how we use it for communicating our results to our colleagues. And yeah, we'll see some more stuff after the break.